Hello everyone, myself Vinay Kumar. I am pursuing PhD in physics. So in this particular YouTube channel, I'll be teaching physics, chemistry and mathematics starting from 8th standard till 12th standard. So if you want to learn physics, chemistry and mathematics, then please do subscribe to my channel. So in my previous video, I had explained about fundamental theorem of arithmetic and examples 1 to 4. And I have also explained all the questions in exercise 1.1. So now in this particular video, we'll move into the next concept which are there after exercise 1.1. So after exercise 1.1, you have the next theorem in this chapter, that is theorem 1.2. So in theorem 1.2, it states that let P be a prime number. So if we take a prime number which is known as P, then that P, if it is dividing A square, then the same P should divide A as well. And A is a integer which is a positive integer. So now if P divides A square, then P divides A, that we have to prove. So now let us consider A as a composite number, a positive integer which has prime factors. So the prime factors of A, let us call them as P1, P2, P3 up to Pn. So that means here we are considering the prime factors of A. And what will be the prime factors of A square? So A square will be simple. It will be P1, P2, up to Pn into P1, P2, up to Pn. So that means here we are considering prime factors of A. So the square of those prime factors will give you A square. So if you multiply all these prime factors, you'll get A. If you multiply that twice, then you'll get A square. So that means here, if you see, A square has P1 2 times, P2 2 times, P3 2 times, Pn 2 times. So 2 times the factors are there. So that means here you can write this as P1 square, P2 square, up to Pn square. So now the prime factors of A square is P1 square, P2 square, Pn square. So that means for A square also P1, P2, Pn are prime factors, but the power is 2. That's it. But in A, we have P1, P2, P3 up to Pn. So these prime factor, this is the prime factors of A, and P1 square, P2 square up to Pn square is the prime factors of A square. So now based on this, according to fundamental theorem of arithmetic, so here according to fundamental theorem of arithmetic, I'll write FTA, that means fundamental theorem of arithmetic. So according to fundamental theorem of arithmetic, all the composite numbers will be having unique factorization. So that means here if A has P1, P2 up to Pn as its prime factors, then that will be unique for A. A square is getting divided by P. So that means P is also a prime factor of A square, and prime factors of A square is P1 square, P2 square up to Pn square. And here P is also the prime factor of A square. So that means this P is in this. So that means here A square also has prime factors which is P1, P2 up to Pn. So square of them. So again P1, P2 up to Pn. So that means here prime factors of A square is also P1, P2 up to Pn. Only thing is they are repeating 2 times because of we are taking A square. So that means here A square is also having prime factors P1, P2 up to Pn, and here P is also the prime factor of A square. So that means in this P1, P2 up to Pn, P is also there. So in this P is also there, because if you look at the statement, P divides A square. P divides A square means P is also the prime factor. Here according to our assumption, P1, P2 up to Pn are the prime factors of A square, and in the question they have given P is dividing A square. So that means this P is also the prime factor of A square, and because of fundamental theorem of arithmetic, this factorization should be unique. So that means P is not separate, P is not outside this, P is inside this. So here that means A square has P1, P2 up to Pn as its prime factors, and P is also dividing A square. That means P is also a prime factor of A square. So that means here P1, P2, P3, Pn up to Pn, what prime factors we have taken now, in that itself P is also there. So P is not excluded out of this group, P is included in this group. So that means here A also has prime factors P1, P2 up to Pn. In this also P should be there, because here P is there in A square, so P should be there in this also, because factorization is unique for a particular number. P is the prime factor which is included in this P1 to Pn range. Similarly, here also P is included in this P1 to Pn range, means P is also the prime factor of A. So that's why, according to fundamental theorem of arithmetic, here P square A is also the factor of A is also factor of, so sorry, P is also the factor of A. So that means here P divides A. So P divides A, you get a rational number. So here if P divides A, you get a rational number. So the symbol for rational number is capital Q. That's it. So this is just for your reference I have given. So generally it means that P is also the factor of A. That is what they had asked in this theorem, and we have proved that. Using this particular theorem, you have to solve the next theorem, that is theorem 1.2. So sorry, theorem 1.3. So in theorem 1.3, you have to prove that root 2, you have to prove that root 2 is irrational. So how to prove root 2 is irrational? In order to prove root 2 is irrational, first we have to assume that root 2 is a rational number, and we have to see whether we get any contradiction. So if we get any contradiction while solving this, then the initial assumption is wrong. That is, if we assume that root 2 is rational number, then that will be wrong. Then it will be irrational number. So what do you mean by irrational number? Irrational numbers are those numbers which cannot be expressed in the form of P by Q. Because if I express in form of P by Q, you have to get a rational number as an answer. But here you won't get rational number as answer. For example, if I consider pi is nothing but 22 by 7. So the answer for this is 3.142, and it goes on like this. You don't get any recurring numbers after decimal point, and you also get different unique numbers keep on repeating itself. So that means here there is no recurring numbers after decimal point, and it is never ending. So that's why pi is a irrational number. So just I am explaining you what you mean by irrational numbers in order to understand this question. So now we have to prove that root 2 is a irrational number. So first we will assume that root 2 is a rational number. Here root 2 can be expressed in the form of P by Q. So root 2 can be expressed as P by Q, where Q is not equal to 0. So if root 2 is a rational number, then we will consider two co-primes. What do you mean by co-prime? Co-prime means, so one concept we have to remember, co-prime are the two numbers which doesn't have any common factors. For example, if I consider 9 and if I consider 4, then 9 and 4 are co-primes, because 9 can be written as 3 into 3, 4 can be written as 2 into 2. They don't have any common factors. Because they don't have any common factors, or they'll be having only 1 as their common factor, because 3 into 3 into 1 you can write, here also 2 into 2 into 1 you can write. So other than 1, they don't have any other common factors. So that's why 9 and 4 are known as co-prime. So this is just co-prime example. So just to make you understand what you mean by co-primes, I have explained this. So now we will take A and B as two co-primes. So we will take A and B as co-primes. So here A and B are the co-primes. So now we will consider root 2 is equal to A by B, where A and B are co-primes. So now we are considering root 2 is equal to A by B, where here B is not equal to 0. So always remember B is not equal to 0. So now we have considered that root 2 is equal to A by B, where A and B doesn't have common factors, they are co-primes. So now root 2 can be expressed as, because root 2 is rational number, that's why I can write this in the form of A by B, that is two co-primes. Or else if this was an irrational number, I couldn't write like this. Remember that. But in the question we have assumed that root 2 is a rational number, so that's why I can write this as A by B. So now root 2 into B, I am taking this B to LHS, so it comes when it comes to LHS it becomes multiplication. So root 2B is equal to A. Squaring on both sides. So squaring on both sides will give me root 2B square is equal to A square. So that means here B square is equal to A square by 2. So that means 2 divides A square. So therefore 2 divides A square. So 2 divides A square. So therefore 2 divides A. This is according to theorem 1.2. So just now we have looked into theorem 1.2 in the previous question. So according to theorem 1.2, if 2 is dividing A square, then 2 divides A. So here 2 is dividing A square, so that's why 2 also divides A. So now we have proved 2 divides A. Therefore A by 2 is equal to C. This is some integer. So C is some integer. So here when 2 divides A, we get one number C, which is an integer, because here we already proved 2 is dividing A. So now 2 divides A square, 2 divides A. That means when A is divided with 2, we'll get one number. Let's assume that number as C, which is an integer. So here first we'll assume 2B square is equal to A square as equation 1. So now we have got A by 2 is equal to C. This I'll write in the next slide. So A by 2 is equal to C. Now you can square this on both sides. So square on both sides. So squaring on both sides will give us A square by 2 square is equal to C. C square. So this you can write as A square is equal to 2 square C square. So A square, in the previous slide you can see, in the previous slide A square is equal to 2B square. So from equation 1, we have A square is equal to, so from equation 1 we have A square is equal to 2B square. So 2B square. So this we will call as equation 2. So now according to equation 1, A square is equal to 2B square. So now equation 2 you can write this as 2B square, or first I will write what is equation 2. So equation 2 is A square is equal to 2 square C square. So this you can write as 2B square is equal to 2 square C square. So now 1 2 gets cancelled with each other. So that means we are getting B square is equal to 2C square. So that means here 2 is also dividing B square. So therefore 2 divides B square. So here 2 divides B square. According to theorem 1.2, 2 also divides B. This is according to theorem 1.1. Theorem 1.2. So according to theorem 1.2, 2 also divides B. So in the previous slide we had proved that 2 divides A, and here we are proving that 2 divides B. So that means here 2 divides A. So here 2 is dividing A. So 2 divides A, and 2 also divides B. So 2 divides B. So here 2 is also dividing A and 2 is also dividing B. So this is what we have proved now. So this cannot happen. But why this cannot happen? We know that A and B are co-primes. So if A and B are co-primes, then how can 2 can divide A and 2 can divide B? Because A and B are co-primes, that means here A and B only have 1 as its common factor. So A and B has 1 as its common factor. Other than 1, there are no common factors for A and B. But here we are proving that 2 is dividing A and we are also proving 2 is dividing B. So that means A also have 2 as the prime factor and B also has 2 as the prime factor. If A and B has 2 as its prime factor, then whatever we have taken here, that is A and B are co-primes, will be wrong, because it cannot have one more factor common. But here one more factor is becoming common. But we have taken A and B are co-primes. So if we have considered A and B as co-primes, then the assumption what we have made is wrong. That means here root 2 is not a rational number. Root 2 is an irrational number. So that means here we are getting contradiction. Here we have taken A and B as co-primes. But here we have proved that A and B are not a co-primes. So that means we have considered A and B as co-primes, but we are getting A and B as not a co-primes. So that means here, therefore, our assumption as root 2 is rational is wrong. So the main assumption what we have taken in the initial stage, that itself is wrong, because we are getting a contradiction. So therefore if root 2 is not a rational number, so therefore root 2 is not a rational number. Therefore root 2 is irrational number. So that means here we have assumed that root 2 is rational number, and by taking A and B as co-primes, we have proved that A and B are not co-primes. So we have contradicted our assumption itself. So that's why our assumption is wrong, that is root 2 is rational number is wrong. And we have, if root 2 is not rational number, then root 2 will be irrational number. So this is how you have to prove using theorem 1.2. So this is all there in this particular video. The examples which are there after this theorem 1.3, I'll be teaching that in my next video, and in that video I'll also try to start the exercise 1.2 questions as well. Until then, if you want to learn more physics, chemistry and mathematics starting from 8th standard till 12th standard, then you have to subscribe to my channel. Please do subscribe to my channel and stay tuned with my channel. Thank you.